Hello, in this lecture we'll find out the area of a circle. In the drawing we have quadrilateral ABCD, and inside this quadrilateral we have this circle. We know that side AB of the quadrilateral is equals to 2 units, side BC equals to 8 units, side DC also equals to 8 units. This is angle ABC that is equals to 90 degrees, and this is also angle DCB that is equals to 90 degrees in its size. Again, our mission is to find out the radius of this circle. So, first of all, we'll do a construction. That is to say, we'll extend side DA and side BC of this quadrilateral ABCD until they touch each other. And we define the touching point of the extended side AD with the extended side BC as point M. We'll define this angle. It's actually angle DMC as angle theta. We know that BC is one side of quadrilateral ABCD, therefore it is absolutely a straight line. When we extended the straight line CB by straight line, the result is CM. When you extend the straight line by straight line, the result must be also a straight line. So CM is a straight line, and we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So the sum of the angles will focus on the upper side of the straight line CM at point B. Here the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So this missing angle, that is angle ABM, must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles on the upper side of the straight line CM at point B to 180 degrees, the missing angle here must be equal to 90 degrees in its size. We'll focus on the right angle ABM. On the right angle ABM, this angle equals to 90 degrees. This angle equals to 90 degrees. This angle equals to theta. Therefore, the missing angle here must be equal to 90 degrees minus theta. Why? Because if we focus on the right angle ABM, the sum of the angles must be equal to 180 degrees. So 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the big right triangle DCM. In the big right triangle DCM, this angle equals to theta, this angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta according to the same logic. Okay. In the next step, we prove that the big right triangle, triangle MDC, is similar to the small right triangle, triangle MAB. I repeat again, we prove that the big right triangle MDC is similar to the small right triangle, triangle AMB. Okay, so I write it down. The big right triangle MDC is similar to the small right triangle AMB. This small right triangle. So, why those two right triangles similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So, this is angle DCM in the big right triangle DCM. And it is equals to this angle that is actually angle ABM in the small right triangle ABM. And again, angle DCM in the big right triangle MDC is equals to angle ABM in the small right triangle AMB. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself is a common angle that belongs to both triangles. So if we relate to angle theta as it belongs to the big right triangle DCM, it will be defined as angle DMC. And it is equals to itself. So if we relate to angle theta as it belongs to the small right triangle ABM, it will be defined as angle AMB. Repeat again. This equation means that angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle CDM in the big right triangle MDC. And it is equals to this angle in the small right triangle ABM. It is actually angle AMB, MAB, the angle MAB. Repeat again, angle CDM in the big right triangle MDC equals to angle MAB in the small right triangle AMB. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So I should prove that all the three angles in the right big triangle DCM are correspondingly equal to all the three angles in the small right triangle AMB. Therefore those two right triangles can similar to each other according to angle, similarity rule. So I write it down. The big right triangle MDC is similar. This is the sign of similar to the small right triangle AMB according to angle, similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side DC in the big right triangle DCM over side AB in the small right triangle AMB equals to side MC in the big right triangle DCM over side MB in the small right triangle AMB. Repeat again. We derive that DC over AB equals to MC over MB. DC equals to 8 units in its length here according to what is given as the question over AB. AB equals to 2 units in its length and it is equals to MC. MC in total equals to MB plus BC. That is to say MC equals to MB plus BC, that is 8. So in total MC equals to MB plus 8. So we substitute MC by MB plus 8. Here MC equals to MB plus 8 over MB. So in conclusion, found out that 8 over 2 equals to MB plus 8 over MB. 8 over 2 is 4, so 4 equals to MB plus 8 over MB. Here we multiply this equation by MB and we get that 4 times MB equals to MB plus 8. Here we subtract MB from this equation. 4MB minus MB is 3MB, so 3MB equals to 8. Here we divide this equation by 3 and finally we get that MB equals to 8 over 3 units in its length. So this is side MB, that is equal to 8 over 3 units in its length. In the next step, we'll focus on the right small yellow triangle A and B. And we will implement the Pythagoras theorem in this right small triangle A and B. Here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. the hypotenuse in this right triangle ABM is AEM, so therefore the square of the hypotenuse is AM squared, and it must be equal to AB squared plus MB squared. So in conclusion, we found out that in the right small triangle AMB, AM squared equals to AB squared plus MB squared. So AM squared, that is the square of the hypotenuse in the right triangle AMB, equals to AB squared. AB is 2, therefore here AB is 2, so therefore AB squared is 2 squared, that is 4, plus MB squared. We just right now found out that MB equals to 8 over 3, therefore MB squared is 8 over 3 squared, that is actually 64 over 9. So in conclusion, we found out that AM squared equals to 4 plus 64 over 9. Here we multiply 4 by 9 and then we will divide it by 9 in order to have a common factor with 64 over 9, and we get that AM squared equals to 4 times 9 is 36 plus 64 all divided by 9. 36 plus 64 is 100 divided by 9. In conclusion, we found out that AM squared equals to 100 over 9. Here we take a root out of this equation, and finally we get that AM equals to the square root of 100 over 9. That is to say, the square root of 100 is 10, and the square root of 9 is 3. So in total, found out that AM equals to 10 over 3 units in its length. The hypotenuse AM equals to 10 over 3 units in its length, so I'll write it down. This is the hypotenuse AM, this is equals to 10 over 3 units in its length. Okay, so in the next step we will do a construction. Actually, we will draw perpendicular on BC in such a way that it will be also tangent to this circle. Okay, repeat again. We will draw perpendicular on BC in such a way that it will be also tangent to this circle. It is absolutely possible to do it. Why? Because you can do the perpendicular on BC in any point on BC. We have infinite points that we can draw perpendicular on BC. So we can choose the perpendicular in a point that it will be also tangent to this circle. Okay. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular and the side BC as T. We'll define the point of tendency of the perpendicular with this circle as point S. We will extend the perpendicular TS until it touches side AD. We define the touching point of the extended perpendicular TS with side AD as point H. We'll define the center of this circle as point O. we define the point of tendency of tangent BT with this circle as G. We define the point of tendency of tangent AB with this circle as K. We join points O and G together by a straight line. Point O is the center of this circle. Point G is the point of the circle itself. Therefore, OG is the radius of this circle. We'll define the radius of this circle as x. Therefore, OG equals to x. It is the radius of the circle. We have here rule number 1, rule 1. That you can implement in our drawing. According to rule 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have tangent AB, that is tangent to this circle, is point M. Point M is the point of tendency, and we have the radius OM, that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. So actually implement all our in our drawing. In our drawing, we have the radius OG that is drawn to point G, that is the point of tendency of tangent BT with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BT will be perpendicular to the radius GO. If BT is perpendicular to GO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and S together by a straight line. OS is the radius of this circle that is equal to x according to our definition. Again, we have the radius OS that is drawn to point S, therefore according to rule number 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. So inside quadrilateral OSTG, inside this quadrilateral, the small quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 degrees times 3 is 270 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size in order to complete the sum of the angles in this quadrilateral to 360 degrees. The missing angle must be equal to 90 degrees. According to the rule, the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees. So inside quadrilateral OSGT, we have 4 right angles. Therefore, we can relate to quadrilateral OSGT as a rectangle. And you know that the opposite sides of a rectangle are equal to each other. That is to say, OG equals to ST. But OG is x, therefore ST must be also equal to x. Likewise, in rectangle OSGT, side OS must be equal to side GT according to the rule that the opposite sides of a rectangle are equal to each other. But OS equals to x, therefore GT must be also equal to x units in its length. So actually found out that quadrilateral OSGT is not a rectangle but a square. Why? Because all of its sides are equal to each other. Okay. Likewise, we join points O and K together by a straight line. OK is the radius of this circle is equal to x according to our definition. Again, we have the radius OK that is drawn to point K. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So inside quadrilateral OGBK, this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the same rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So, quadrilateral OGK, quadrilateral BGKO, this quadrilateral has 4 right angles. Therefore, we can relate to this quadrilateral as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, side OG must be equal to side KB. But OG equals to x, therefore KB must be also equal to x. Likewise, according to the same rule, side OK must be equal to side BG. But OK equals to x, therefore BG must be also equal to x units in its length. So again, we found out that quadrilateral OKBG is not a rectangle but a square. Why? Because all of its sides are equal to each other. In conclusion, we found out that line segment BT, this is line segment BT, that is equal to x plus x, that is 2x. So BT equals to 2x in its length. I write it down. BT equals to 2x. In the next step, we'll focus on the right triangle HTM. In this right triangle HTM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Only what I've already explained, that the sum of the angles in a triangle is equal to 180 degrees. So the missing angle equals to 90 degrees minus theta in its size. In the next step, we will prove that the right big triangle HTM is similar to the right small triangle AMB. So I write it down. We'll prove that the right triangle HTM is similar to the right small triangle ABM. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this is the angle HTM in the big triangle HTM. And it is equal to this angle that is actually angle ABM in the small right triangle ABM. Repeat again. Angle HTM in the big right triangle HTM equals to angle ABM in the right triangle ABM. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, this is a common angle, it belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to angle theta as it belongs to the big right triangle HTM, it will be defined as angle AMT. And it equals to itself. So if we relate to angle theta as it belongs to the small right angle A and B, it will be defined as angle A and B. Repeat again. This equation means that angle theta equals to itself as a common angle that belongs to both angles. We just call two angle theta two different terms. Okay, and finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle MHT in the big right angle HTM. And it equals to this angle, that is actually angle MAB in the big triangle, in the small right triangle ABM. This is angle MAB. Repeat again. Angle MHT in the big right triangle HTM equals to angle MAB in the right small triangle ABM. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the big right triangle HTM are correspondingly equal to all the three angles in the small right triangle ABM. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. The big right triangle HTM is similar to the small right triangle ABM according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that edge T in the big right triangle HTM, side HT in the big right triangle HTM, over side AB in the small right triangle ABM, equals to side TM in the big right triangle HTM over side BM in the small right triangle ABM. Repeat again. HT over AB equals to TM over BM. And also side edge M in the big right triangle HTM over side AM in the small right triangle AMB. Repeat again. We found out that HT over AB equals to TM over BM equals to edge M over AM. HT is the missing side, so we'll leave it as it is, over AB. AB equals to 2 units in its length according to what is given as the equation, so we will substitute AB by 2, and it is equals to TM. TM, from the drawing it is very easy to see that TM or MT in total equals to MB plus BT. So MT in total equals to MB, that is 8 over 3, plus BT, that is 2x. So in total, MT equals to 8 over 3 plus 2x. So we substitute mt by 8 over 3 plus 2x. Here, we substitute tm by 8 over 3 plus 2x over bm. bm or m bit is the same, it is 8 over 3. So we substitute bm by 8 over 3, and it is equals to edge m equals to edge a plus am. That is to say, edge m equals to edge a plus am, that is 10 over 3. So in total, edge m equals to edge a plus 10 over 3. So we substitute edge m by edge a plus 10 over 3. Here edge m equals to edge a plus 10 over 3 over am. am equals to 10 over 3. It is the hypotenuse of the right triangle BM. It is equals to 10 over 3 units in its length. So we substitute am by 10 over 3. So we have here a long equation. Those two sides, they are equal to each other, so we get the first equation from those two sides that are equal to each other. That is to say, edge t over 2 equals to 8 over 3 plus 2x over 8 over 3. Here we'll multiply 2x by 3 and then we'll divide it by 3 in order to overcome factor with 8 over 3. And we'll get that ht over 2 equals to 8 over 3, and 2x times 3 is 6x. So it is, this expression equals to 8 plus 6x over 3 divided by 8 over 3. So in conclusion, found out that ht over 2 equals to 8 plus 6x over 3 plus 8 over 3. Here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. After we cancel 3, we left only with ht over 2, that is equals to 8 plus 6x over 8. So ht over 2 equals to 8 plus 6x over 8. Here we will multiply this equation by 2, and we get that ht equals to 8 plus 6x, and we multiply this equation by 2, so 8 over 2 is 4. So we will find out that ht equals to 8 over 4 is 2 plus 6x over 4 is 1.5x. In conclusion, found out that line segment ht equals to 2 plus 1.5x units in its length. So here ht this line segment ht equals to 2 plus 1.5x in its length. We return to the long equation. This is the long equation. Those two sides, they are equal to each other. Therefore, we get equation number 2 from those two sides that are equal to each other. So 8 over 3 plus 2x over 8 over 3 equals to edge A plus 10 over 3 over 10 over 3. Again, we multiply 2x by 3 and then we divide it by 3 in order to overcome a factor with 8 over 3. And we get that 8 over 3 plus 2x times 3 is 6x over 3 equals to, and divided by 8 over 3, and it equals to, here we multiply edge A by 3 and then we divide it by 3 in order to overcome a factor with 10 over 3. So edge A times 3 is 3 edge A plus 10 over 3 divided by 10 over 3. So we have here 3 in the numerator and 3 in the denominator, so 3 will get cancelled. Here also we have 3 in the numerator and 3 in the denominator, so 3 also will get cancelled here. And in common we found out that 8 plus 6x over 8 equals to 3 edge A plus 10 over 10. Repeat again. Actually found out that 8 plus 6x over 8 equals to 3h plus 10 over 8 over 3h A plus 10 over 10. Here we cross multiply this equation and we get that 10 times 8 plus 6x equals to 8 times 3 edge A plus 10. Here we divide this equation by 2 and we get that 10 over 2 is 5, so it is 5 times 8 plus 6x, that is equals to 8 over 2 is 4, so it is 4 times 3 edge A plus 10. We'll open the brackets on both sides of this equation and we get that 5 times 8 is 40 plus 5 times 6x is 30x. This equals to 4 times 3 edge A is 12 edge A and 4 times 10 is 40. So here we have 40 on both sides of the equation, so 40 will get cancelled and we're left only with 30x, that is equals to 12 edge A. So here we'll divide this equation by 12 and finally we'll get that edge A equals to 30x over 12 is 2.5x. edge A equals to 2.5x in its length. Here, this side edge A equals to 2.5x units in its length. Okay. In the next step, I will copy quadrilateral ABTK, this quadrilateral, in a new page with the circle that is inscribed inside it, and we will analyze this quadrilateral ABTK, ABTH, quadrilateral ABTH. Okay. So actually, this is quadrilateral AHBT that I copied from the original drawing. We will define the point of tendency of tangent AT with this circle as J. We define the point of tendency of tangent AH with this circle as K. We define the point of tendency of tangent AB with this circle as T. We can actually implement rule number 2 in our drawing. I will run you quickly what is rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. We have a circle in the drawing and the common standpoint point P. From the common standpoint point P, we have two tangents to the second, tangent PA and tangent PB. According to this rule number 2, rule 2, PA equals to PB. The lengths of those two tangents that exist from the common standpoint are equal to each other. PA equals to PB. We can implement rule 2 in our drawing. Why? Because if we focus on the common standpoint point A, from the common standpoint point A, we have two tangents to this circle, tangent AT and tangent AK. Again, tangent AT and tangent AK. And according to rule number 2, they are equal to each other. That is to say, AT equals to AK. Repeat again. If we focus on the common standpoint point A, from the common standpoint point A, we have two tangents to the circle, tangent AT and tangent AK, and according to rule 2, they are equal to each other. That is to say, AT equals to AK. So if we define one of those two tangents as A, then the other tangent must be also equal to A because they are equal to each other. Okay. So if tangent AK equals to A units in its length, then tangent AT must be also equal to A units in its length because they are equal to each other. Okay, likewise, we'll focus on the common start point, point B. From the common start point, point B, we have two tangents to this circle. Tangent, here we will define the point of tendency of tangent BT with this circle Sn. So from the common start point, point B, we have two tangents to this circle, tangent BT and tangent BN. And according to rule 2, they are equal to each other. That is to say, BT equals to BN. So according to the sum rule 2, if we focus on the common start point, point B, tangent BT equals to tangent BN. So if we define one of those two tangents as B, then the other tangent must be also equal to B because they are equal to each other. Repeat again. If tangent BT, the length of tangent BT equals to B units, then the length of tangent BN must be also equal to B units because they are equal to each other. In the next step, we will focus on the common start point, point C. From the common start point, point C, we have two tangents to this circle, tangent Tn and tangent Tj. And according to rule 2, they are equal to each other. Repeat again. If we focus on the common start point, point T, tangent Tn must be equal to tangent Tj according to rule 2. So if we define one of those two angles as C, then the other angle must be also equal to C because they are equal to each other. So here, if the length of tangent Tn is C, then the length of tangent Tj must be also equal to C because they are equal to each other. And finally, we'll focus on the common external point, point H. From the common external point, point H, we have two tangents to this circle, tangent HJ and tangent HK. And according to rule number 2, to rule 2, they are equal to each other. That is to say, HK equals to HJ. Repeat again, according to rule 2, if we focus on the common start point, point H, tangent HK must be equal to tangent HJ. So if we define one of those two tangents as D, then the other tangent must be also equal to D because they are equal to each other. So I write it down. So if we define the length of tangent HK as D, then the length of tangent HJ, then the length of tangent HJ must be also equal to D units in its length because they are equal to each other. Okay. In the next step, we will add side AB to side HT. And again, AB plus HT. We actually add the two opposite sides of quadrilateral AHBT. So AB plus HT. AB plus HT. What is the value of AB plus HT? From the drawing it is very easy to see that AB equals to A plus B. Plus HT. From the drawing it is very easy to see that HT in total equals to C plus D. So in conclusion, we found out that side AB plus side HT of quadrilateral AHBT is equals to A plus B plus C plus D. In the next step, we will add the two opposite sides of quadrilateral AHBT. We will add side AH to side BT. AH plus BT. What is the length of side AH in total? Is A plus D. What is the length of side BT? Is B plus C. So in total, AH plus BT equals to A plus B plus C plus D. Repeat again, it is very easy to see from the drawing that AH plus BT in total equals to A plus B plus C plus D. Okay. So in conclusion, we found out that AB plus HT equals to A plus B plus C plus D, and AH plus BT also equals to A plus B plus C plus D. And from those two equations, we will derive that AB plus HT equals to AH plus BT. Okay? AB plus HT equals to AH plus BT. AB equals to 2 units in its length. AB equals to 2, so we substitute AB by 2 plus HT. HT in total equals to 2 plus 1.5x, so we substitute HT by 2 plus 1.5x. And it is equals to AH. AH equals to 2.5x, so we substitute AH by 2.5x plus BT. BT in total equals to x plus x, that is 2x. So we substitute BT by 2x. So in conclusion, we found out that 2 plus 2 is 4. So it is, in this side of the equation we have in total 4 plus 1.5x, that is equals to, on the other side of the equation we have 2.5x plus 2x is 4.5x. So in conclusion, we found out that 4 plus 1.5x equals to 4.5x. Here we subtract 1.5x from this equation, And finally we will get that 4 equals to 4.5x minus 1.5x is 3x. So in total we found out that 4 equals to 3x. Here we will divide this equation by 3, and finally we will get that x equals to 4 over 3 units. That is to say, the radius x of this circle equals to 4 over 3 units in its length. Repeat again. The radius x of the circle equals to 4 over 3 units in its length. Now, it is very easy to see, to find out the area of the circle. The area of any circle equals to pi r squared. The area, according to our definition, the radius of this circle is x. So the area of any circle is pi times the radius squared. The area of our circle equals to pi times the radius squared. And the radius is x, therefore the radius squared is x squared. So the area of our circle is pi x squared, and x is 4 over 3, so it is pi times x, that is 4 over 3 squared, because it is x squared. So pi times 4 squared is 16, over 3 squared, that is 9. So in conclusion, we found out that the area of our circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equals to 5.585 square units. Repeat again. The area of this circle, the area that we are looking for, equals to either 16 pi over 9 square units, or in terms of numbers, the area of this circle equals to 5.585 square units. Okay, and that is the answer to the question. In the next step, I will summarize the lecture. In this lecture, we found out the area of this circle. So, in the drawing, we have quadrilateral ABCD. In the drawing, we have quadrilateral ABCD, and inside this quadrilateral ABCD, we have a circle. Our mission is to find out the area of this circle. In addition, we know that side AB of quadrilateral ABCD equals to 2 units in its length, side BC equals to 8, side DC also equals to 8 units in its length. This is angle ABC that is equal to 8 units in its size, to 90 degrees. Angle ABC equals to 90 degrees in its size, and this angle DCB also equals to 90 degrees in its size. Again, our mission is to find out the area of this circle. So, first of all, we did the construction. That is to say, we extended side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. This is their touching point. We defined their touching point as point M. Then we defined this angle as theta. So in the right triangle, big triangle DCM, this angle equals to theta, this angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the right triangle ABM. Here, actually, why this angle equals to 90 degrees? Because BC is one side of quadrilateral ABCD, therefore it is absolutely a straight line. BC is a straight line. When you extend the straight line BC by straight line, the result is CM. When you extend the straight line by straight line, the result must be a straight line, so CM is also a straight line. CM is one straight line. So if we focus on the upper side of the straight line CM at point B, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is 90 degrees, plus the missing angle, that is angle ABM. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that I mentioned. Therefore, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of CM at point B to 180 degrees, the missing angle here must be equal to 90 degrees. So this angle is a right angle, therefore triangle ABM is a right angle. So in the right angle ABM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta, according to the same logic that this angle equals to 90 degrees minus theta. In order to complete the sum of the angles in this right angle to 180 degrees, the missing angle here must be equal to 90 degrees minus theta in its size. Then we proved that the small right angle ABM is similar to the big right angle DCM. Why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both angles, so we can write down that angle theta equals to itself. It's a common angle that belongs to both angles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually prove that all the angles of the right big triangle DCM are corresponding equal to all the angles of the right small triangle ABM. Therefore, those two right angles can go into each other, are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side DC of the big triangle over side AB of the small triangle equals to side CM of the big triangle over side BM of the small triangle. Again, repeat again. We will derive that DC over AB equals to MC over MP. DC is 8, AB is 2. What is the length of MC? MC in total equals to MB plus BC. That is to say, MC equals to MB, that is MB plus BC, and BC is 8. So in total, MC equals to MB plus 8. Yeah. MC equals to MB plus 8 over MB. 8 over 2 is 4, so 4 equals to MB plus 8 over MB. Here we multiply this equation by MB, and finally found out that 4 times MB equals to MB plus 8. Here we subtracted MB from this equation, and finally found out that 4 MB minus 1 MB equals to 3 MB. So 3 MB equals to 8. Here we divided the equation by 3, and finally found out that MB equals to 8 over 3 units in its length. Here MB equals to 8 over 3 units in its length. Here 97 MB equals to 8 over 3 units in its length. Then we focus on the right triangle, small triangle ABM. We implemented the Pythagoras theorem in this right small triangle ABM. Only to the Pythagoras theorem in this right triangle ABM. AM square equals to AB square plus BM square. Again, AM square equals to AB square plus MB square. So AM square, that is the square of the hypotenuse, equals to AB square. AB is 2, therefore AB square is 2 squared, that is 4, plus MB square. MB is 8 over 3, therefore MB square is 8 over 3 squared, that is 64 over 9. So AM square equals to 4 plus 64 over 9. Here we multiplied 4 by 9, and then we divided it by 9 in order to have a common factor with 64 over 9. And found out that AM square equals to 4 times 9 is 36, plus 64 over 9. 36 plus 64 is 100 over 9. So AM square equals to 100 over 9. We took out of this equation and finally found out that AM equals to the square root of 100 over 9. The square root of 100 is 10 and the square root of 9 is 3. So in total, we found out that AM, the hypotenuse AM equals to 10 over 3 units in its length. Here, the hypotenuse AM equals to 10 over 3 units in its length. Then, we define the center of this circle as O. We join points O and G together by a straight line. OG is the radius of the circle that we defined as X. The radius OG is drawn to point G, therefore this angle equals to 90 degrees and this angle equals to 90 degrees according to rule 1. We join points O and S together by a straight line. OS is the radius X that is drawn to point S, therefore according to rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. In quadrilateral OGTS, in this quadrilateral we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral OSGT we have 4 right angles, therefore we can relate to quadrilateral OSGT as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side OS equals to side GT. But OS equals to X, therefore GT must be also equal to X. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, side OG must be equal to side SC. But OG is X, therefore SC must be also equal to X. So we found out that quadrilateral OGTS is not a rectangle but a square, because all of its sides are equal to each other. Likewise, we join points O and K together by a straight line. OK is the radius of the circle that is equal to X. The radius OK is drawn to point K, therefore according to rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. So inside this quadrilateral OKBG we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees according to the sum rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So this angle must be equal to 90 degrees. So inside quadrilateral OKBG we have 4 right angles, so we can relate to quadrilateral OKBG as a rectangle. And you know that the opposite sides of a rectangle are equal to each other. That is to say, side OK must be equal to side GB, but OK is X, therefore GB must be also equal to X. Units in its length. Likewise, according to the sum rule, OG must be equal to KB, but OG is X, therefore KB must be also equal to X. So we found out that quadrilateral KOBG is not a rectangle but a square. And in conclusion, we found out that line segment BT in total equals to X plus X, that is 2X. Repeat again, we found out that BT equals to 2X units in its length. Okay, then we did another construction, that is to say, we drew perpendicular on BC in such a way that it will be also tangent to this circle at point S. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction, and the perpendicular that we drew here is also tangent to the circle at point S. We extended the perpendicular until it touches side DA at point H. Okay, in this way we created the right triangle HTM. In the right triangle HTM, this angle equals to 90 degrees, this angle equals to theta, therefore the missing angle must be equal to 90 degrees minus theta. Then we proved that the right triangle HTM is similar to the right small triangle ABM. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I actually proved that all the three angles of the right big triangle HTM are correspondingly equal to all the three angles of the right small triangle ABM. Therefore, we proved that those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive that side HT on the big triangle over side AB in the small triangle equals to side TM on the big triangle over side BM on the small triangle. Again, HT over AB equals to TM over BM, and it is also equals to side edge M in the big triangle over side AM in the small triangle. Repeat again. We will derive that HT over AB equals to TM over BM equals to HM over AM. HT over AB. AB is 2, so we will substitute AB by 2. What is the length of TM? TM in total equals to 8 over 3 plus 2x. Okay? So substitute TM by 8 over 3 plus 2x. BM equals to 8 over 3, and it is equals to edge M. Edge M is the edge M. Here edge M is actually edge A plus AM. That is to say, edge M in total equals to edge A plus AM, that is 10 over 3. So in total, edge M equals to edge A plus 10 over 3. Here we substitute edge M by edge A plus 10 over 3 over AM. AM is 10 over 3. AM is 10 over 3, so in conclusion, we found out that 8 HT over 2 equals to 8 over 3 plus 2x over 8 over 3, and it is also equals to edge A plus 10 over 3 over 10 over 3. Those two sides are equal to each other, so we created equation number 1 from those two sides that are equal to each other. So according to equation number 1, HT over 2 equals to 8 over 3 plus 2x over 8 over 3. Here we multiply 2x by 3 and then we divide it by 3 in order to overcome a factor with 8 over 3. And we found out actually that HT over 2 equals to 8 plus 6x over 3 over 8 over 3. Here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. And we left only with HT over 2, that is equals to 8 plus 6x over 8. Here we multiplied this equation by 2 and finally found out that HT over 2 times 2 is HT. And we have 8 divided by 2 is 4, so we found out that 8 plus 6x over 4 equals to HT. So HT equals to 8 over 4 is 2, and 6x over 4 is 1.5x. So in total, we found out that HT equals to 2 plus 1.5x. Here, this line segment HT equals to 2 plus 1.5x. Then we return to our log equation, and we found out that we have those two sides are equal to each other, so we created equation number 2 from those two sides that are equal to each other. Okay. So we found out that 8 over 3 plus 2x over 8 over 3 equals to HA plus 10 over 3 over 10 over 3. Here we multiplied 2x by 3 and then we divided by 3 in order to overcome a factor with 8 over 3, and found out that 8 plus 6x over 3 equals 8 plus 6x over 3 over 8 over 3. Here we multiplied HA by 3 and then we divided by 3 in order to overcome factor with 10 over 3, and found out that 3HA plus 10 over 3 equals to 10 over 3HA plus 10 over 3 over 10 over 3 equals to 8 plus 6x over 3 over 8 plus 8 over 8 over 3. Here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. Here also we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. And finally found out that 8 plus 6x over 8 equals to 3HA plus 10 over 10. Here we cross multiplied this equation and found out that 10 times 8 plus 6x equals to 8 times 3HA plus 10. We divided this equation by 2 and found out that 8 over 2 is 5, so we have 5 times 8 plus 6x equals to 8 over 2 is 4, so in this side of the equation we have 4 times 3HA plus 10. Here we open the brackets on both sides of the equation and found out that 5 times 8 is 40, plus 5 times 6x is 30x. In the other side of the equation we have 4 times 3HA is 12 edge A, plus 4 times 10 is 40. We have 40 on both sides of the equation, so 40 we can cancel. Then finally found out that 30x equals to 12 edge A. Here we divided this equation by 12 and finally found out that edge A equals to 30x over 12, that is 2.5x. So edge A in total equals to 2.5x. Here, this line segment edge A equals to 2.5x. Then I copied this quadrangle AH BT with its circle and realized this quadrangle AH BT. This is the quadrangle AH BT that I copied from the original drawing. Implemented here rule number 2. From the common standpoint, point A, we have two tangents to this circle, tangent AT and tangent AK. And according to rule number 2, they are equal to each other. That is to say, AT equals to AK. Here, AT equals to AK. So if we define one of those two tangent as A, then the other side, the other tangent must be also equal to A because they are equal to each other. So if AT is A, then AK must be also equal to A. Then focus on the common standpoint point B. From the common standpoint point B, we have two tangents to the second, tangent BT and tangent BN. According to rule 2, they are equal to each other. So BT equals to BN. Again, according to rule 2, BT equals to BN. So if we define one of those two tangents as B, then the other tangent must be also equal to B because they are equal to each other. So if BT equals to B, then BN must be also equal to B because they are equal to each other. Then we focus on the common standpoint point T. From the common standpoint point T, we have two tangents to this second, tangent TN and tangent TJ. And according to rule number 2, they are equal to each other. That is to say, TN equals to TG. Yeah. In the common standpoint point T, TN equals to TG. So if one of those two tangents equals to C units in its length, then the other tangent must be also equal to C units in its length because they are equal to each other. So if Tn equals to C, then Tj must be also equal to C. And finally, we focus on the common standpoint point H. From the common standpoint point H, we have two tangents to this circle, tangent HK and tangent HJ. And according to rule number 2, they are equal to each other. That is to say, HK equals to HJ. The common standpoint point H, HK equals to HJ. So if one of those two tangents is D, then the other tangent must be also equal to T because they are equal to each other. So if HK equals to D, then HJ must be also equal to D because they are equal to each other. Then we added side AB to side HT in quadrangle AHBT. AB plus HT. AB is A plus B and HT is C plus D. So in total, AB plus HT equals to A plus B plus C plus D. Then we added side AH to side BT. AH plus BT in total equals to A plus B plus C plus D. Again, AH plus BT equals to A plus B plus C plus D. So we found out that AH plus HT equals to A plus B plus C plus D, and AH plus BT also equals to A plus B plus C plus D. So from those two equations, we derived that that AB plus HT equals to AH plus BT. Those two expressions must be equal to each other because they have the same value. Therefore, AB plus HT must be equal to AH plus BT. AB is 2, HT is 2 plus 1.5x, AH is 2.5x, and BT is 2x. So in conclusion, we found out that 2 plus 2, that is 4, so 4 plus 1.5x equals to 2.5x plus 2x, that is 4.5x. Here we subtracted 1.5x from this equation, and finally found out that 4 equals to 4.5x minus 1.5x is 3x. So 4 equals to 3x. 4 equals to 3x. We divided this equation by 3 and finally found out that x, that is the radius of the circle, equals to 4 over 3 units in its length. Here the radius of this circle x equals to 4 over 3 units in its length, and the area of any circle is pi times the radius squared. In our, according to our definition, the radius of our circle is x, therefore it is pi times x squared. x is 4 over 3, so it is pi times 4 over 3 squared. And it is pi times 4 squared is 16, over 3 squared that is 9. So in conclusion, we found out that the area of this circle, the area that we are looking for, equals to either 16 pi over 9 square units, or in terms of numbers, the area of this circle equals to 5.585 square units. Okay, thank you very much.